Let's revisit the dot product and see how it is consistent with everything we've been doing right now, or up to now. Recall the component notation of a particular vector A, which you can write as axi plus ayj. We have seen that if you want to write a vector in component notation, you have to figure out the ax and ay scalars, which can be obtained easily by taking the magnitude of the vector times the cosine of the angle, if the angle is measured from the positive x going counterclockwise, and similarly ay can be obtained by taking the magnitude of the vector times the sine of the angle. Now let's recall the dot product. I have drawn here my vector A, and I have drawn here my unit vector I and j. Let's imagine that I would like to take the dot product between A and I. All I have to do is project my vector A along the direction of my unit vector I, and I need to do it in such a way that it is perpendicular to it. So this must be by definition A, which is the magnitude of vector A, times 1, which is the magnitude of my unit vector I, times cosine of the angle. Therefore, A dot I is A cosine theta. And this is a scalar. This is this distance right here. Now, if I would like to express the vector going from here to here, which we used to call ax, then really ax is nothing different than the magnitude of my vector times the unit vector, as we've said before. This ax must be the length of this vector ax, which happens to be a cosine theta. So really, what we've been doing before by projecting any vector in the x direction and by taking the magnitude of the vector, which we used to call hypotenuse, and taking this, multiply it by the cosine of the angle to obtain what we used to call the adjacent, or whatever jargon you used to use when you use Pythagoras, is actually nothing else than doing the dot product. This is also known as the unit vector notation, because it takes any vector and can be expressed as its magnitude times, in general, its unit vector. So this is the most general form, E being the unit vector in any direction. If you're looking for, if the vector f happens to be in the x direction, then this will be f x is equal to fx scalar times I. If f happens to be in the y direction, fy vector is equal to fy j, whatever direction you want to pick. Now the beauty of this notation is that you can actually project the vector in any axis. You're not stuck and restricted to using the x-axis or the y-axis. For instance, if you have a vector A, same vector as before, but this time instead of projecting this vector A along the x, which we already know how to do, let's pick a random direction, L. And I would like to project vector A along this direction L. Therefore, I would like to know this vector, which I will write A parallel to my direction L. How am I going to get this? Well, I can use the same technique. I know that if this is the angle between my two vectors, all I need to do to calculate the component of A, which is parallel to my direction L, is to take my original vector A and dot it with the unit vector, which is a line along L of length 1, which I will call E. This will give me a scalar, which happens to be this exact length. But since I want a vector, I need to multiply this scalar the same way as we do with the x, back with the unit vector again. Therefore, I need to multiply this by E again. So really, all I need to do is either know the angle, and I can just replace this by a cosine theta, or if I know 2 points on my line, say point C and point D, of coordinate dx, dy, C being cx and cy, I can update the position vector CD. By definition, CD is dx minus cx, dy minus cy. I can obtain and calculate the unit vector of that position vector. Now remember, if a vector has any length, in my case CD, and I would like the unit vector which is parallel to CD, it's going to be a vector which is parallel, but its length will be equal to 1. So the same way as we wrote before, AX is equal to AX times I. We could solve for I, which is nothing else than the vector AX divided by its own magnitude. So we can use the same technique. In this case, my vector E is nothing else than my full vector CD divided by its own magnitude. Now since I know the vector CD, position vector CD, which is dx minus cx plus dy minus cy, I can calculate its magnitude. All I need to do is take this term, square it, take this term, square it, add them up, take the square root, and I will end up with the magnitude CD. So CD will be square root of dx minus cx squared plus dy minus cy squared. So that will give me a number. All I need to do is take my original CD vector divided by this number, and that will give me my unit vector E, which in turn I can plug here, calculate the dot product with my vector A. If I'm being given the component addition, I can do that. I just multiply all the x component together, I multiply all the y component together between A and E, I add them up. This will give me the magnitude of my vector, and I just need to multiply this scalar by my unit vector again. Now the nice thing about this technique is, now if I would like to figure out this component, all I need to do, I'm sorry, not y, I'm going to call it a perpendicular. Since I know A, and by now I know A parallel, if I would like to figure out A perpendicular, since A is equal to A parallel plus A perpendicular, then really all I have to do is solve for A perpendicular, which will be vector A, my original vector, minus the parallel component that I've just calculated, and this will give me A perpendicular. Since this vector and this vector in component addition, it's no brainer. So again, this functional form of the dot product is the one that we have actually used all along, except we have a line and taken the simple case where the unit vector is I or j. But really, you can use the same technique in any direction and project your vector in any coordinate system, which is nice. So now you know that you're not stuck with a standard coordinate system x, y like this when you're dealing with vector, you can project it to, say, another coordinate system of your choice, x prime, y prime, and instead of projecting it as ax and ay, you can do the same thing with your new coordinate system, ax prime, ay prime, and you can obtain both ax and ay using this nice little formula.